which has been asked in various competitive exams, during board exams also. But before we go into those questions, solving those questions, let us first discuss certain tips and tools for solving critical questions. Right? So first of all, we'll be discussing a few different types of questions, and we'll be finding out shortcuts to those questions and questions and circuit diagrams, and then we'll go into the numericals. Right. So our very first type is case 1. Our very first type is OLAs of small drops of liquid. Small drops of liquid into bigger drops. So now in this type of question, you will be given a certain number of small drops of liquid, and using those small drops of liquid, you will be forming a bigger drop of liquid. And finally, you will be asked that what should be the charge acquired by that bigger drop, what is the potential acquired by that bigger drop, and finally the capacitance value of the bigger drop. Okay. For the algorithm, we will assume, let's say that this is a single small drop of liquid, and say that he is having a charge Q. Q is the small q is the charge of the single drop of liquid, and we say that we are having n number of such drops. Okay, so this n number of small drops, its goal is to form a bigger drop. And since we are talking about the single drop, so let's say that R is the radius of small single drop. Okay, so this is the radius of a single small drop, and with the help of this radius, we'll be finding out the radius of the bigger drop. Now, since we are talking about a drop of liquid which is spherical in shape, so the volume of bigger drop will be nothing but n times the volume of smaller drop, right? Since we are using these small drops, which are n in number, and you are using this drops of liquid to form this bigger drop, so that is why the volume of the bigger drop will be n times the volume of the smaller drop. Alright. Now, since they are spherical in shape, so the volume will be 4 by 3 pi capital R cube. So R is the radius of the bigger drop, and which is nothing but n times the volume of the smaller drop, which is nothing but 4 by 3 pi small r cube. So when you cancel out this 4 by 3 pi and 4 by 3 pi, so you get the relation between the radius of the bigger drop and the radius of the smaller drop, which is nothing but n to the power 1 by 3 r. So this is the relation between radius of bigger drop and the radius of smaller drop. Okay, this is equation number 1. Now, since the small drop, the single small drop, is having a charge Q, so charge of the bigger drop, let's say it is capital Q, it will be nothing but n times the charge of the small q. Okay, so because you are not having extra charge, whatever charge you are having, that is provided by this n number of single drops. Okay, and how you will find out the charge of the charge acquired by the bigger drop? It will be nothing but n times the charge of the smaller drop. So you can put this equation number 2. Now our third point is we will be finding a potential of this bigger drop. So for this, what we will do, we will recall the potential expression for a spherical shell. Like we have done this, that when we consider a spherical shell, what should be the potential acquired by the spherical shell. So let's say that you are having, this is a spherical shell, okay, and he is having a charge q at the surface. So, earlier topics were already studied that since for a spherical shell, for a conducting shell, since the electric field inside it is 0, so the potential becomes constant there. We studied this, and that constant value is nothing but the potential at the surface. That means whatever amount of potential we will have at the surface, the same potential we will have inside the shell. Now, if he is having a charge q, so at the surface we will have a potential of this much, 1 by 4 pi epsilon naught q by capital R. Now, R is the radius of this shell. Okay, so we will be using this relation, this expression of potential, to find out what should be the potential of this small single drop and the potential of this bigger drop. Okay, for this, what we will do, first we will find out the potential of a single drop of liquid. Now, since this single drop of liquid is having radius r, so and he is having a charge q, so potential of a small drop of liquid, which will be same as what we had done a few minutes back, that is potential of spherical shell. So that same expression will come across. So we will have it as 1 by 4 pi epsilon naught q by small r. This is the radius of that small drop, and this q is the charge given to that small drop. Okay, let's say that it is nothing but v suffix small s. So this will tell you the potential for that small drop of liquid, a single small drop of liquid. Now, since these small drops are used to form a bigger drop, so again the bigger drop is it is a spherical in shape with having radius capital R. So let's say that V suffix B. Now this is the potential of bigger drop of liquid, so which will be same as 1 by 4 pi epsilon naught capital Q. Now in place of the small q, we will have capital Q, because we have already seen, right, few minutes back, that the charge acquired by the bigger drop, which is nothing but n times the charge of the single drop, and we have already seen that radius of the bigger drop, it is nothing but 10 to the power 1 by 3 times the radius of the smaller drop. So we are going to use these two relations to find out the potential of the bigger drop divided by capital R. This is the radius of the bigger drop. So 1 by 4 pi epsilon naught. So you replace this q value with this expression, which is nothing but n small q, and the radius of the bigger drop, it becomes n to the power 1 by 3 r. So when you do the simplification, you get something like this: 1 by 4 pi epsilon naught q by small r. Remember, this is the expression of potential of that single drop, small single drop, and it is multiplied by a certain factor. We're going to find that. So the potential of the bigger drop, so when you do the calculation, it turns out to be something n to the power 2 by 3 times, and this is the potential of that single drop, small single drop, potential of the small single drop. Right? So this is the expression or relation between potential of the bigger drop, and the bigger drop is formed by using n number of small drops, who is having a charge q and potential Vs. This is the relation between the bigger drop and the potential of the bigger drop and potential of the smaller drop. So you can make a third point here: potential of bigger drop is nothing but n to the power 2 by 3 times potential of the smaller drop. So, okay. So here I am writing out all the points there. So when you will be solving numericals, you don't need to go through all these steps. If you can remember this expression, final expression, it will help you to solve such type of questions in a few minutes. Okay, so this is how you are going to find out the potential of the bigger drop. And our last point is to find out the capacitance value of that bigger drop. Okay. So for that, what we are going to do, we will be using the relation between charge, capacitance, and potential. And then we'll be using this Q value and V value, and then finally we'll be finding a relation, the expression for the capacitance of the bigger drop. Now we have this relation, like Q equals to CV. We have already studied this. Now when we find the capacitance expression, it is nothing but Q by V. Right? Now if I want to know for bigger drop, let's say that we are going to first of all find out the capacitance for smaller drop. Okay, so for smaller drop, our capacitance expression will be nothing but Q by V suffix x. Okay, now this Q is the charge acquired by a small single drop of liquid, and this Vs, V suffix s, is nothing but the potential acquired by that single drop, small single drop. Because of which the C suffix s is nothing but the capacitance value of that small drop. Now for bigger drop, C suffix B, let's say this is the capacitance of that bigger drop, and for bigger drop we have already seen that Q is the charge acquired by that, so we will replace it by Q, and the potential of the bigger drop is nothing but V suffix B, so we will keep it as that only, V suffix B. So this is the capacitance expression of the bigger drop. When we replace all this Q and V potential value, okay, so we will see the final expression for the capacitance. Alright. Now when you simplify this n factor, so it is nothing but 1 minus 2 by 3. And if you see this part, Q by V suffix s, this is the capacitance value of that small drop. Right? All we need to do is just to solve this that n factor. So when we solve it, so we get something into the power 1 by 3 times the capacitance of the smaller drop. This is our final expression. C suffix B is nothing but n to the power 1 by 3 times C suffix s. So these are the few final expressions which will help you to solve such questions. Okay, if you find any type questions like where you will be given small drops of liquid, where you require with the number of the small drops of liquid, and you'll be asked to form a bigger drop, and then finally you will be a question to find out what is the charge of the bigger drop, or sometimes there are questions where you'll be asked and find the ratio of that potential of the smaller drop and the potential of the bigger drop. Okay, so in that way also the question has been asked. So you don't need to go through all these steps, because this is not going to carry as that data marks there. So if you can remember this 4 formulas, 4 expressions, so it will take a very less amount of time and you can solve this question very easily. Okay. So in our second step, I will be discussing the circuit diagram, and how you are going to redraw the circuit diagram, and then how you are going to find ineffective capacitance of the particular circuit diagram. So it is, question will be like this, you will be provided with 3 capacitors. Okay. Now these 3 capacitors, they are in series, but they will change this circuit diagram by connecting a branch here, 2 branches there. This will be one branch and this will be the second branch. Okay. So this will be our circuit diagram where you are having 3 capacitors, C1, C2, C3. So if you see this circuit diagram, in this all these three capacitors, different currents are flowing. Okay? Because it is connected with the different branches there. So we will just simplify this by drawing it in this form. Since different currents are flowing through these three different capacitors, so this entire circuit, it is nothing but can be redrawn it into this form. Okay. So you can connect all these three capacitors into parallel connection. Okay. So this circuit diagram is completely equivalent to this circuit diagram. Now, when you see the circuit like this, it might create a confusion. So, if you can remember how you can draw the equivalent diagram for such circuits, so this will really help you to find out your equivalent capacitance. Now, since this C1, C2, C3 they are connected in parallel, so easily you can use a parallel formula, and that is nothing but C1 plus C2 plus C3, and with the help of this relation, you will be able to solve such circuit diagram. So this is our case 2. Similar, there is another case 3, where it has been asked, the question has been asked in this way. Let's say that this is point X, and we will provide a circuit diagram like this. Let's say that this is C1, and here you will be having another capacitor. Let's say it is C2, and in this branch you will be having C3. This is how the circuit diagram will be given to you. Now again, if you see this here also, different currents are flowing through these different capacitors. So how you can draw the equivalent circuit diagram for such circuits? So again, what you will do, you will just draw this as parallel combination of these three capacitors, C1, C2, C3. So this is the equivalent circuit diagram for such circuits, right? So in this way, again, you will be able to find your effective capacitance, which is nothing but C1 plus C2 plus C3. Okay. So these are the two types of circuit diagram which has been asked a number of times there. Now, in the fourth case 4, here what we will do, we will consider 4 capacitors. Let's say this is capacitor 1, second capacitor, third capacitor, fourth capacitor. Okay, let's say that we consider another fifth capacitor. So it seems that these 5 capacitors are connected in series. Now what I will do here, I will connect a wire from this point to this point. Again, I will connect a wire from this point to this point. Okay. This is a certain branch of wire which is connected between this capacitor. So say that this is capacitor C1, this is C2, this is C3, this is C4, and this is C5. So if you see carefully this circuit diagram, you can draw it in this manner. Let's say that this is point A, and from point A, let's say that this is point B. Okay. So from this point A to point B, you are having capacitor C1. Now we have drawn the equivalent capacitance of this circuit, right? And it was case 2 where we have drawn the equivalent capacitance of this circuit. So there we had studied that these 3 capacitors are connected in parallel because they are connected between different points there, and different charges flowing all these three capacitors. If I would not have connected this wire here and this wire here, then same charge would have flown through all these three capacitors C2, C3 and C4. But since I have connected a wire there, so what will happen, and since there is no potential drop across this wire, okay, so different charges, that means different current is actually going to flow through all these three C2, C3 and C4 capacitors. So what we will do, we are going to draw a parallel combination of these three capacitors. Three capacitors, C2, C3 and C4. And from this end, let's say that this is point C. So from this end, you will have a capacitor C5, which is connected to this point. Okay. So let's say that this is point D, connected to this point D. So this is C5. Alright. So now if we draw the equivalent circuit for this one, so we can redraw this again in this one. Let's say that this is point A, where you are having capacitor C1, and the equivalent capacitance of these three parallel combination of capacitor, let's say it is C dash, and we are having E5 there to this point B. So the equivalent capacitance of this final setup will be nothing but 1 by C1 plus 1 by C dash plus 1 by C5, where C dash is equals to C2 plus C3 plus C4. Right. So this is how we are going to redraw this circuit diagram. Right. Now there is another circuit diagram where capacitors are connected. Okay, let's say that this is point M, and let's say that this is point M. From here, from this end, another capacitor is connected to this end. Okay. And this end, another capacitor is connected, and on this end, fourth capacitor is connected. Okay, so this is another circuit diagram. Let's say that this is C1, this is C2, this is C3, and this is C4. Now, how we are going to redraw the equivalent circuit for this diagram? Now, if I consider that this is positive terminal, and let's say that this is negative terminal. Now, since here, if you see this part, now there is no potential difference. So there is no potential drawing device connected to this part. So that is why this point, which is M, so this end will also have same potential, that is M. Okay. Again, if you see this part, this branch, if you see, so there is no potential drawing device is connected. So that is why in this branch, this wire, now there is no potential draw. So because of which, this point will also have same potential. That is why I am writing M there. Okay. Since you are not having any potential drop across this branch, so that is why at this junction I have written here as M. And in this branch, there is no potential drop. Just a wire is connecting. That is why this point will also have that same potential M. Similarly, if you see this end, N is written here. And if you see this branch, there is no potential drop. So this junction will also be M. Okay. And this junction you can put it as the letter T here. Right? So how we are going to redraw this? Now if you see from this point M, two branches are coming out and they are getting connected to this point P. So what I will do, from this point M, I will take two branches. This is my first branch, let's say capacitor C2, and this is connected to this point P. Okay. Again from this point M, because all these 3 points are having same potential, which is M. So from this point M, C3 capacitor is connected to this point P. C3 capacitor is connected to this point P. Okay. Now if you see point P and N, the capacitor is connected there. So from point P to point N, C1 capacitor is connected. And if you see again, there is a capacitor connected in parallel between M and N, which is C4. So you can connect a capacitor C4 here to this point N, C4. So this is how we can draw an equivalent circuit diagram for such circuits. Now easily if you see this, these two capacitors are connected in parallel, and it is in series with this C1, and again this equivalent capacitance of this 2 and C1, they are connected in parallel to this C4. Alright, so this is my point N. Let's say that C dash is nothing but equivalent capacitance of C1 and C2 and C3. This is in series with C1, and again it is parallel to C4. This is my point N. Right? So in this way, if you use C dash, it is nothing but, since parallel combination, it is nothing but C2 plus C3. And again, if you redraw this, so again you will see from here, if you redraw this, so again you will see that you will have a capacitor C double dash, which is in parallel to C4 between the terminals M and N. Right? So in this way you will be able to solve this. Now your net capacitance CA net, it is nothing but 1 by C4 plus 1 by C double dash. Now C double dash is nothing but the equivalent capacitance of C1 and C dash. So C double dash is nothing but C1 multiplied by C dash by C1 plus C dash. This is my C double dash value. So you replace the C dash and C double dash value in this final equation, and you should be able to find your equivalent capacitance. Alright. So this circuit is very important, because this is the basic equivalent circuit, and we have drawn this from this one in the given circuit. Alright. Now another circuit diagram. It is something like this. Like, let's say that this is point M, and here you connect two capacitors in this branch, and it is leading to this point N. Let's say that they are having identical capacitors, so that is a CC, capacitance of each capacitor. And here also two identical capacitors are connected. Alright. Now from this, let's say that this is let's say that you are drawing diagonals for this particular rectangle. So you are connecting two capacitors in this diagonal and two capacitors, identical capacitors, in this diagonal. So C, 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 C. So you are having 1, 2, 3, 4, 5, 6, 7, 8 capacitors connected in this form. And you see that here you are having a common point O for this diagonal capacitors. Now if you see this end, let's say that this is my positive terminal, and let's say that this is my negative terminal. If you see this branch, there is no potential drop. So you can easily assume that this point is M, and similarly you can assume that this point is M, because there is no potential drop here. So that same potential will exist at this 2 amps. Similarly, this is my point M, negative terminal. Here you can see that there is no potential drop. So that is why this terminal or this junction will have same potential M, and this junction will have same potential M. Alright. As you can see there are two capacitors between M and M. Right? Here there are two capacitors, and in this branch also there are two capacitors between M and N. And from M to this point O, there are two capacitors. And from again N, there are two capacitors to this point O. So these two capacitors. If I want to draw the equivalent circuit diagram, so what I will do, let's say that this is my point M. So here we are having two capacitors between M and N, right? So what we will do, we will draw two capacitors. We draw two capacitors to this point N. Let's say this is C. And here also there are two capacitors between M and N. So we'll draw two capacitors here between M and N. Again, from this point M to this point O, there are two capacitors C and C. These two capacitors are there. What we will do, this is my first capacitor, and this is my point O, and the other capacitor from this point M, from this point M to this point O. See, these are the two capacitors. Right? Similarly, from point N, we are having two capacitors, this two, to this point O. So that means O is a common point for these four capacitors. So let's say that this is again a point O. So you connect this capacitor C to this point N, and you connect this capacitor C to this point M. Right? So this is the equivalent circuit diagram for this circuit. And what we will do, as you can see here, that these two capacitors are connected in series. These two capacitors are connected in series. They are connected in parallel. They are connected in parallel. So we can easily redraw this again. And here you will have an equivalent capacitance of this parallel capacitor. Let's say that it is C dash and C double dash. E, C, C, C. Alright. Now these two capacitors are in series. Now let's say that it is C1, equivalent capacitance for this first branch, upper branch. So it will be C multiplied by C divided by 2C. So it's around C by 2. So the equivalent capacitance of this two capacitor is C by 2. Similarly, the equivalent capacitance of this two capacitor will also be C by 2. Right? So let's say that it is C3. That means for this branch, the equivalent capacitance is C3 and this one is C1. Right? So same two capacitors or capacitance C is connected, so that is why this will also be C by 2. Now for C2, that means for the middle branch, we are having two capacitors C dash and C double dash which are connected in series. So it will be C dash and C double dash by C dash plus C double dash. And both this C dash and C double dash, they are nothing but 2C. C double dash, okay, it is 2C. When you calculate this, you will find a capacitor of capacitance C. Alright? You will have a capacitor of capacitance C. So when you find your net capacitance, there will be nothing but 1 by C1 plus 1 by C2 and 1 by C3. Okay, sorry, so this they are connected in parallel. So you will be having a parallel equation So C net will be equals to C1 plus C2 plus C3, because this is my equivalent capacitance C1. From the middle branch you will have capacitance C2, which is nothing but C, and for the third branch you will have capacitance C3, so C by 2. Now since they are connected in parallel, so that is why you will be using a parallel formula, C by 2 plus C plus C by 2. You will find an equivalent capacitance of 2C. So that means the equivalent capacitance of this circuit diagram is 2C. Alright? Okay, so now in the next type, what we will do, we will consider these metal plates. Let's say that this is metal plate 1, this is metal plate 2, and this is metal plate 3. And all these three metal plates, they are equidistant from each other. Okay? They are equidistant from each other. Let's say that we assume that that the separation between all these three metal plates, 1, 2, 3. The separation between all these three metal plates is D. So D is the separation. Separation between each metal plate. And then what I will do, I will connect metal plate 1 and 2 metal plate 1 and 2, sorry, 1 and 3 I will connect to the positive terminal. Let's say it is connected to the positive terminal of the battery, and metal plate 2 is connected, let's say it is connected to the negative terminal. Let's say that it is point X and this is point Y, connected to the negative terminal. Alright? So again I will repeat what I am doing it here. So I will consider three metal plates A, B, C, D, E, F. Three metal plates are considered, and they are placed at equidistant from each other, and the separation between them is D. And what I have done, I have connected metal plate 1 and 3 to the positive terminal X, and this metal plate, second metal plate, I have connected to the negative terminal. So that means this plate is positive now, and this plate number 3, is positive. Right? Because it is connected to the positive terminal. So they will have same potential, positive potential. And the second plate is connected to the terminal, negative terminal. So that is why he will have a negative potential there. Right? So it behaves, so and you will be asked to find equivalent capacitance. Equivalent capacitance of such arrangement. This is what you will be asked. Right? So how you can do this? So this arrangement, this is equivalent to a parallel combination of two capacitors. Right? So this is equivalent to a parallel combination of two capacitors. Let's say that this is point X and this is point Y. Right? Now we know that for a parallel plate capacitor, we have this capacitance expression, which is nothing but absolute naught A by D. Right? Since here also we are having metal plates there, and which are arranged in parallel form, right? Parallel position we have arranged it. and we have connected this first and third to a positive and the second to the negative terminal. So this arrangement can be redrawn into two parallel combinations, and we have to separately find the capacitance of these two capacitors. Now if I find capacitance of this C1, it is nothing but absolute naught A by D, because for this two metal plates AB and CD, they are having same area, plate area is same, and the separation between them is D. So that is, and the vacuum medium between these plates is vacuum. That is why you are having a capacitance C. And for this second arrangement, the CD and EF, right? So the capacitance of this second arrangement, again it is nothing but epsilon naught A by D, because the plate area is same and the separation between them is D. Alright? So if I find the equivalent capacitance, it is nothing but C1 plus C2. So that should be something 2 epsilon naught A by D. Alright? So this is how we find equivalent capacitance of such arrangement. Okay. Now here again what I will do, I will consider metal plates. This is one metal plate. I consider another metal plate. Right. So these are my two metal plates, and each of them is separated by equal distance. Okay. Right, and they are having that same area A. Now what I will do here, I will connect the first metal plate and the fourth metal plate. Okay, I'm going to connect this two metal plate to the positive terminal. So that is this point X and this is my positive terminal. And I will connect this second metal plate and this third metal plate to the negative terminal. Let's say that this point is Y. Okay, this is my first, second, third, fourth. Remember, all of them are separated by the distance. Separation is the D between two plates. Okay. So now as you can see here, since first and fourth plates are connected to the positive terminal, so both of them will have higher potential, and second and third is connected to the negative terminal. So this second and third plate will have lower potential. So this arrangement, for this arrangement, when we will be finding out effective capacitance, so it is nothing but a parallel combination of two subcapacitors. Okay, so if you see this first part and if you see this last part, that means if you see first plate and second plate, this is behaving like a capacitor, parallel plate capacitor, and if you see the third plate and fourth plate, this is behaving like a parallel plate capacitor. Right? So the equivalent capacitance of such arrangement of plates is nothing but the parallel combination of two subcapacitors. So what I will do here, this will be my first capacitor C1 and this is my second capacitor C2. Remember, we are seeing this first part, that means this region we are considering. This region we are considering. This region is behaving like a parallel plate capacitor, and this region is behaving like a parallel plate capacitor. Okay, so that is why we state that it is nothing but parallel combination of two capacitors. Alright, so for C1, so it is nothing but epsilon naught A by D, since the plate area is A and the separation between them is D for this first arrangement. And for the second arrangement, it is also same, which is epsilon naught A by D. So when we find our equivalent capacitance, that is C net, so it is nothing but C1 plus C2, and which will be same as 2 epsilon naught A by D. Okay, so in this case, what we will do, we will consider 4 plates, and all these 4 plates will be connected with different terminals. Okay, but in this case, what we will do, we will connect only our first and the third plate. We are going to connect this to the terminal X. Now he is positively charged, and we are going to connect our second and fourth plate to terminal Y, and that is negatively charged. Alright. Now, if you can see, now since this first and third plates are connected to positive terminal, they acquire positive potential. Right? That means they are at high potential. And the second and fourth plates are connected to the negative terminal, so they acquire negative potential. That means they are at lower potential. Alright. So we see an arrangement, a parallel arrangement of 4 parallel plate capacitors. Right? So this is one parallel plate capacitor, arrangement of parallel plate capacitor. Right? Then we have an arrangement of parallel plate capacitor in the middle, and then we are having another parallel arrangement of parallel plate capacitor in the lower region, right? So all these 3 parallel plate capacitors, they are connected, or we can say they are arranged in parallel combination. So if we redraw this, so we can consider 3 capacitors, parallel plate capacitors, connected in parallel combination between the terminals X and Y. Right? So we are going to use the parallel plate capacitance expression, which is nothing but epsilon naught A by D, right? Because they are having a separation of D during each plate. Right? Between these two, they are having D separation between these two D, and between these two, they are having that same D distance. D. And all these metal plates are having this same area here. Right? So when we are finding out our equivalent capacitance, so it is nothing but 3 C, right? If I consider the capacitance of this 3 C, and for each of them it is nothing but epsilon naught A by D. So our final equivalent capacitance is going to be 3 epsilon naught A by D. Alright, this is how we can find capacitance for such arrangement. Okay, so in this case, what we will do, we will consider 4 plates, and all these 4 plates will be connected with different terminals. Okay, but in this case, what we will do, we will connect only our first and the third plate. We are going to connect this to the terminal X. Now he is positively charged, and we are going to connect our second and fourth plates to terminal Y, and that is negatively charged. Alright. Now, if you can see, now since this first and third plates are connected to positive terminal, they acquire positive potential. Right? That means they are at high potential. And the second and fourth plates are connected to the negative terminal, so they acquire negative potential. That means they are at lower potential. Alright. So we see an arrangement, a parallel arrangement of two parallel plate capacitors. Right? So this is one parallel plate capacitor, arrangement of parallel plate capacitor. Right? Then we have an arrangement of parallel plate capacitor in the middle, and then we are having another parallel arrangement of parallel plate capacitor in the lower region, right? So all these three parallel plate capacitors, they are connected, or we can say they are arranged in parallel combination. So if we redraw this, so we can consider three capacitors, parallel plate capacitors, connected in parallel combination between the terminals X and Y. Right? So we are going to use the parallel plate capacitance expression, which is nothing but epsilon naught A by D, right? Because they are having a separation of D between each plate. Right? Between these two, they are having D separation between these two D, and between these two, they are having that same D distance. D. And all these metal plates are having this same area here. Right? So when we are finding out our equivalent capacitance, so it is nothing but 3 C, right? If I consider the capacitance of this 3 C, and for each of them it is nothing but epsilon naught A by D. So our final equivalent capacitance is going to be 3 epsilon naught A by D. Alright, this is how we can find capacitance for such arrangement. Alright, so till now we have discussed few types of questions of capacitors, and how to find the equivalent capacitances. Now we will start solving various questions which have been asked in various exams. Right? So here, if you see this question, there are three capacitors, and each one is having a capacitance of 9 microfarad. Right? So here, since C1 is equals to C2 is equals to C3, and we can take it as C, right, having this 9 microfarad. And in how many ways, you have to find out in how many ways all these three capacitors can be arranged, and what should be the value of the effective capacitance. Right? So let's say that this is our first arrangement. So we will keep it very simple. So we will first connect all the three capacitors in series. Right? Let's say that this is C1, C2, and C3. Now, since we have studied that when capacitors are connected in series, to find out your net capacitance, what you do, you express it something like this. Alright, so this is how you find your equivalent or effective capacitance of capacitors which are connected in series. And in this case, all the three capacitors are having same capacitance value, so we'll take it as C. We have already mentioned it earlier. So it will be like 1 by C plus 1 by C plus 1 by C. So it becomes 3 by C. And this C value is around 9 into 10 to the power minus 6, 9 microfarad. Okay. So we are having like 1 by 3 into 10 to the power minus 6. So this is 1 by C net. So when you find your effective capacitance, so it is something 10 to the power minus 6 farad. Alright, so this is our first arrangement, and this is the effective capacitance of this arrangement. Now we'll go to our second arrangement. So here what we will do, we will connect all the capacitors in parallel. And when capacitors are connected in parallel, this is how we find the effective resistance, effective capacitance. What we do, we just add all this capacitor value. Right? So C nav is equal to C1 plus C2 plus C3. This is how we find effective capacitance of capacitors which are connected in parallel. And we'll get a C plus C plus C, so it becomes around 3C. So it is nothing but 9 microfarads. So 10 minus 6 farad, 18 microfarad. Alright, so this is our second arrangement in net.
Okay, so here there is a mistake there. It should be 27 microfarad. I have written it as 18 microfarad. It should be 27. Please correct this.
The third arrangement, we can arrange it like this, like, two of the capacitors can be connected in series, and the other one can be connected like this. Okay, the two capacitors which are connected in series, that arrangement is in parallel with the third one. Right, so in that way also we can arrange our capacitors. So for these two capacitors, we have to find our C, let's say C dash. Like C dash is the effective capacitance of these two capacitors which are connected in series. So it is something like C plus C, C into C plus C plus C. This is how you find. Like you do that same thing. 1 by C dash is equals to 1 by C plus 1 by C. So you get something C by 2. Right. So C by 2 is around 9 by 2. Okay, so C dash is something 4.5 microfarad. Alright, so this is the effective capacitance of these two capacitors which are connected in series. Now these two capacitors are connected in parallel to this third one. So our C net will be nothing but C dash plus C. Now C dash is 4.5 microfarad plus 9 microfarad. Right? So you get around 13.5 microfarad. So this is our C net value. This is how you arrange. The third way to arrange these three capacitors. Okay. Now there is another way how you can arrange these three capacitors. Now in this case, third case, what we have done, we have taken the two capacitors we have taken in series and it is in parallel with the third capacitor. Now what we will do, we will take two capacitors and they will be parallel to each other. Two capacitors are parallel to each other and their effective is in series to the third one. Okay, let's say C, C and C. So we have to find effective capacitance of these two capacitors which are connected in parallel. Let's say that it is C dash. It is nothing but 2C. Right? So when capacitors are connected in parallel, so you just add those capacitance value. And to find your C net, what do you do? Again you do that because the C dash is in series to this third capacitor. So we proceed with that same earlier formula, like 1 by C net is equals to 1 by C1 plus 1 by C2. Now in this case, in case of C1 we will be using C dash, and in case of C2 we will be using C. Right, so C dash multiplied by C dash plus C. Okay. So if you rearrange them, so you will get this formula. And C dash is how much? 2. Okay, 2C multiplied by C, again 2C plus C. So you get something 2C by 3. So 2 by 3, now we know this C value, which is again 9 microfarad. Okay, so when you do the calculation, so you get 6 microfarad. Okay, so this is the fourth way to arrange these three capacitors, and this is the effective capacitance of such arrangement. Right? So in this way, you should be able to do. Now, in some case, questions they have asked that they will be providing you that you have three capacitors with each value with some values will be given, capacitance value will be given to you, and you have to find the arrangement. They will provide you effective capacitance value, and they will be asking you how to arrange these three capacitors so that your effective capacitance value will be such. Let's say that effective capacitance value is 4 microfarad. So in what arrangement you will you will arrange your capacitor so that you should get an effective capacitance of 4 microfarad. So in that way also the question has been asked. Let's say that here you are finding your effective capacitance is 6 microfarad, and they will just give you this value, and they will ask you that how we will arrange these three capacitors with each is having 9 microfarad capacitance. You will draw the arrangement of these three capacitors, where you will find 6 microfarad. So you have to draw this arrangement well. Right? This arrangement you have to draw, and you have to say that these two capacitors are in parallel, and that parallel two capacitors, they are in series with the third capacitor. In that way, questions are there. So here, if you see that the circuit is given to us, and the capacitors of the different capacitance value, they are arranged in different manner, and we need to find the resultant capacitance of such arrangement. So if you see capacitors C2 and C3, they are parallel, and C1 and C4, they are connected in series with this parallel arrangement, right? So let's just find our effective capacitance for this parallel arrangement. Let's say that it is C dash. Okay, so C dash is nothing but C2 plus C3 is going to be 6 microfarad plus 6 microfarad. It's around 12 microfarad. So that is C dash. So now this circuit diagram, we can redraw it something like this. This is our C1. Okay, and instead of drawing this parallel arrangement, we can directly write this effective capacitor. And that is C4. And this is C dash. Right? So all these three capacitors now they are arranged in series, so we can find our effective capacitor. Let's say that it is C net, and it is equals to 1 by C1 plus 1 by C dash plus 1 by C4. Now C1 value is known to us, it is again 1 by 12 microfarad. C dash, it is 1 by 12 microfarad, and the C4 is again, it is 1 by 12 microfarad. So 3 multiplied by 1 by 12 microfarad, so it's around 1 by 4 microfarad, right? So that is our 1 by C net, right? So C net, you get effective capacitance here. If you reciprocal it, you will get around 4 microfarad. Okay, so this is how we can solve such arrangement. Okay, so if you see this arrangement, here C1 and C2, this capacitance value is given to us. C1, it is 3 picofarad, so that means 10 to the minus 12 farad. And C2, it is 2 picofarad, that is 2 into 10 to the minus 12 farad. Alright. Now, for this arrangement, we have to find. So, if you see this 3 capacitor, C1, C2, and again this capacitor C1. All these 3 capacitors are arranged in series. Okay. So first of all, we'll find out the effective capacitance of these 3 capacitors. Let's say that it is C dash. Right. Now since they are connected in series, so it will be 1 by C dash is equals to 1 by C1 plus 1 by C2 plus 1 by C1. right? Since they're connected in series. So 1 by C dash. Now C1 is 3 into 3 picofarad, so let's just consider that it is 3 picofarad. 2 is 2 picofarad, and again C1 we have 1 by C1, so it is again 1 by 3 picofarad. Okay. So if we calculate around 2 by 3 plus 2, it will be around 6, so it's around 4 and this 3, so it comes out to be 7 by 6. So the effective capacitance of these 3 capacitors which are connected in series is around 6 by 7. Okay, so by 7 picofarad. Then if we redraw this circuit diagram, is something like this. This is my C1. This will be another capacitor C2, and here we are having capacitor C1. And instead of drawing these 3 capacitors, now we will be drawing the effective capacitors of all these 3, which are arranged in series. Alright. Now this is going to be C dash. Alright. Now remember, students they do a mistake that since they see this picture, this diagram in such a way that this branch where C2 is connected and this branch where C2 is connected, another C2 is connected. They consider that they are parallel, and they use the parallel process for these 2 capacitors. Or they consider that this one is parallel to this one, so they consider that they use the again parallel way, how to find out capacitance when they're connected in parallel. They use that formula and then they do the calculation. This is completely wrong. Okay, so you have to understand the circuit diagram, how these capacitors are arranged, and on that understanding only you have to apply the formulas. Okay, that is why initially we have calculated the effective capacitance of these 3 capacitors which are in series. We have calculated our effective capacitance C dash. Now if you see this branch and if you see this branch, both of them are parallel, right? Because different currents are flowing through this branch and through this branch. So we are going to find again effective capacitance, okay, for these 2 capacitors. We are going to find effective capacitance for C2 and C dash. Now since they are connected in parallel, okay, if you see this capacitor C2 and C dash, since they are connected in parallel, so we will be using parallel formula. And let's just say that the effective capacitance of these 2 capacitors, let's just take it, it is C double dash. So it will be something plus C2 plus C dash, right? Now C2, it's something 2 picofarad. So 2 plus we had 6 by 7 picofarad. Okay, so if you do the LCM 6 and here it is going to be 14, 20 by 7 picofarad. Okay, so when we combine these 2 capacitors, we get effective capacitance of C double dash, which is 20 by 7 picofarad. Now we can again redraw this arrangement, in such a way that this is point A, this is point B. Now we are having a C1, and here we are having C1. Now instead of drawing this arrangement, we will be drawing the effective capacitance. I will be considering one single capacitor with 20 by 7. So this single capacitor is the effective capacitance of these 2 capacitors, C2 and C dash. Okay. Now as you can see in this diagram, these 3 capacitors C1, C double dash and C1, they are connected in series. So now we will be able to find our C net, which is 1 by C1 plus 1 by C double dash plus 1 by C1. Alright. So C1, it is 1 by 3, and this C double dash is 20 by 7. So we'll take it 7 by 20 plus it is again 1 by 3. Okay. So 2 by 3 is 7 by 20. So if you do the calculation, it's around 60, and here 21, and here you'll find 40. Okay, so 1 by C net, something 40 plus 21, so it is going to be 61 by 60, right? And if you reciprocate it, you will get C net, it is 60 by 61. This is how we are calculating the effective capacitance of this arrangement, and we are redrawing it in every step. Now how we can find the effective value for this arrangement, right? So this is our first step. This is our second step, and step by step we are going to we will be able to find out the effective capacitance. So here in this arrangement, the capacitors are arranged. Now you have to find the equivalent capacitance and also calculate the total charge when a battery of 100 volt is connected between the points A and B. Point A and let's say this point B. So you are having different capacitors: C1, C2, C3, C5, C6, C4, and all are having different values, right? Because what we are going to do, we are going to redraw the circuit diagram. I will be able to do that, and then we'll be finding out the effective capacitance of such arrangement, right? If you see this capacitor C2, you see this capacitor C3, and this C4, all these are connected in series. And if you see this C5 and this C6, they are connected in parallel. Okay. So first step, step 1. Now we are going to redraw it. This is point A. This is C1. Here we will divide it in two parts. Here you will be having one capacitor. Let's say that it is C dash. C dash is the effective capacitance of these two capacitors, C5 and C6. And let's say here you are having another capacitor with, let's say, the C double dash, with equivalent capacitance of this C2, C3, and C4 capacitors. Alright. We are going to find step by step this C dash and C double dash value. Since the C dash, they are connected in parallel, right? So it will be just addition of these two capacitors, C5 and C6. C5 is 10 microfarad and C6 is 10 microfarad. So C double dash is going to be 20 microfarad. Right? C dash is 20 microfarad. Remember, we are just using or we are just following, how these capacitors are arranged, okay, in this individual segments of the diagram. And this is how C dash is calculated, 20 microfarad. And to calculate C double dash is the equivalent capacitance of these three capacitors which are connected in series. So we are going to use the series method, which is 1 by C double dash. It is again going to be 1 by C2 plus 1 by C3 plus 1 by C4. Alright, C2 is 60, C3 is 60, and he is also 60. 3 by 60 microfarad, it is going to be around 1 by 20 microfarad. C double dash is equals to 20 microfarad. Okay, 20 microfarad. C1, it is 40 microfarad. Okay. So this is how we have calculated our C dash and C double dash. Now again C dash and C double dash, they are connected in parallel. Different currents are flowing through this uh, two capacitors. So we can again redraw this circuit diagram, and it is going to be something like point A, and here you are having C1, which is 40 microfarad. Since they are connected in parallel, so we are directly, we are going to just write the value here. In parallel connection, you just add the two capacitors values. So when you add them, so it is again, let's just consider that it is C triple dash, and the C triple dash is going to be 40 microfarad. And this connects to terminal B. Alright, our next step. Now last step, they are connected in series. Okay, so we are going to have the equivalent capacitance. C net. This is our equivalent capacitance. Now, since two capacitors are connected in series, we are directly going to solve it. C triple dash by C1 plus C triple dash. Now C1 is 40. So when you multiply this 2, it's around going to be 1600 microfarad. And when you add this 2, 2 into 40 microfarad. T 100. So therefore, our C net is 20 microfarad. Okay. This is our equivalent capacitance. Okay. Now our second question is we have to find the total charge that flows through the circuit when a 100-volt battery is connected to the points A and B. Right. Now, since we have calculated our equivalent capacitance, so now this entire arrangement we can arrange it in a single capacitor instead of considering the number of capacitors. Like we are having 6 capacitors, instead of considering 6 capacitors, we will consider only one capacitor now, and he is having a value of 20 microfarad. Okay. So this arrangement is having an effective capacitance of 20 microfarad. So now that is why we have written it as 20 microfarad. This two terminals A and B will connected with battery. So he is having a potential of 100 volts. We have to find the total charge. So we have this relation Q equals to CV. So 20 into 10 to the power minus 6, 20 micro, and with this 100 volt. So it will be 20 into 10 to the power minus 4 coulomb. This is the amount of charge which is flowing through this circuit, okay, between the point A and B when it is connected with a battery of 100 volt. Okay. Right. So now, okay, if you see this arrangement, we are going to redraw this arrangement first. Okay. So how we are going to redraw this? First, what we will do, we are going to extend from this point X. So let's say that this is my point X. This is the branch which is going from this point S, and it is leading to this point A. This is my point A. And if you see this point A is divided in two parts. This is my first branch where C1 capacitor is there, and this first branch is extending to this point B, and the second branch it is leading to this point D where C3 capacitor is connected. Right. So first we are going to draw these two branches. This is the first branch leading to this point B where C1 capacitor is connected, and this is the second branch where C3 capacitor is connected, and it is leading to this point D. And this point B and point D is connected with this capacitor C5. So you are having this capacitor C5 and it is leading to this point E. Again, if you see from this point D, we are having a branch which is going to this point C, and having this capacitor C4. So from point D, again we start uh, connecting this capacitor C2 to this point C. And if you see that point B and point C is connected, having this capacitor C2. Okay, so this is C4. Sorry. This is C4, right? Between these points B and C. And from point B, you are having a capacitor C2, and it is going to this point C. Right? So this is how you rearrange or redraw this circuit diagram consisting of all 5 capacitors. And once you redraw this in this pattern, then you will see this ratio C1 by C2 and this ratio C3 by C4. That means you will see the ratio of capacitance in this branch AB and BC and the ratio of capacitance in this branch AD and DC. You will check whether these ratios are equal or not. If these ratios are equal, then you will not allow, that means the charge through this branch BD, you will consider it 0. Then there is no charge flow in branch BD. That means there is no charge flow through the capacitor C5. Alright. Then what we will do, since if we see that these ratios are equal, now we will check whether these ratios are equal or not. Now the C1, C2, C3, C4, C5, all these capacitance values are given to us. Now, C1 is 5, C2 is 10. Okay. C1 is 5 microfarad and C2 is 10 microfarad. C3 is 2 microfarad and C4 is 4 microfarad. So if you check the ratio, it turns out to be something 1 by 2 for both the case. Right. So as usual, our ratio of the capacitances are equal. So that means if there is no charge flow through this branch BD. That means there is a potential difference between this point B and B. So then what we will do, we will redraw this circuit diagram in the simple form. Okay, we are going to draw it in this manner. C1, this is C2, this is C3, and this is C4. Remember, since there is no charge flow through this branch, so we have not drawn that branch. Okay, so that is why these two capacitors now they are in series, C1 and C2, and this C3 and C4 they are in series. So we are going to find the equivalent capacitance for this C1 and C2 and equivalent capacitance of this C3 and C4, and finally we will see a parallel arrangement, the equivalent capacitance. Let's say that C dash is the equivalent capacitance of C1 and C2. Now, since they are in series, so we are going to use that series formula. So it will be like C1 into C2 divided by C1 plus C2. Now, C1 is 5 microfarad multiplied by 10 microfarad. Below you will be having 15 microfarad. So it turns out to be 50 by 15. So we get something like 10 by 3. Right. So this is our equivalent capacitance, C dash. So let's just redraw that again. C dash. C double dash. C double dash is the equivalent capacitance of the C3 and C4. We are going to calculate that also. So C dash, this is 10 by 3. Now we are going to find the equivalent capacitance of C3 and C4. So that we have assumed that it is C double dash. C double dash. Okay. So it is again C3 into C4 by C3 plus C4. So C3 is how much? 2 microfarad multiplied by 4 microfarad. And then when you add them, it is around 6 microfarad. So 8 by 6, so it is around something 4 by 3. So C double dash it is 4 by 3 microfarad. Right? Now since C dash and C double dash, they are parallel, so we are going to use parallel formula so that we will find our C net now. Okay, so C net, we are going to use parallel formula, and which is nothing but C dash plus C double dash, and C dash is how much? 10 by 3, and C double dash is 4 by 3. So our equivalent capacitance is something 14 by 3 microfarad. Okay. 14 by 3 microfarad. So this is how we solve such arrangement. Okay. So this is our first step, where we redraw this into this bridge form. This is what we call the bridge form, and then we check whether this ratio are equal or not. So if these ratios are equal, then only we will be able to apply the next step. There is nothing but these two capacitors, they will be in series, and then again they will be parallel to this C3 and C4, and finally we will be able to find out our net capacitance. Okay. So here if you see this diagram, various capacitors are connected, and equivalent capacitance that is given to us. So this is 1 microfarad. That means the equivalent capacitance of this entire circuit that is given to us. We have to find the value of capacitance of this capacitor. This is what we have to find. So for this, what we will do, we will redraw this circuit diagram in the various pattern. So our first step, what we will do, now this is point A, this is our capacitance C, and this is C1, and here we are having C2, and if you see C3 and C4, they are parallel. So we are going to draw an equivalent capacitance, let's say C dash. Now if you see the data given here, C3 is 2 microfarad and C4 is again 2 microfarad. So if you use the formula there, so this C dash will be nothing but 4 microfarad. Okay. Then we continue like this. Then you will be having these two capacitors, they are in series. So you can draw another equivalent capacitance, let's say C double dash. And this C double dash, it is parallel. It's parallel to this C7. Okay. So we have to find C double dash first. So C double dash, which is equivalent capacitance of these two series capacitors, C5 and C6. So C5 multiplied by C6 divided by C5 plus C6. I'm directly doing it. Okay, so C5 is 6 microfarad and C6 is 12 microfarad. So 6 into 12 by 12 plus 6, 18. 72 by 18. Right. So it is 4 microfarad. Yes, there is 4 microfarads. So this C double dash which you see, this is 4 microfarad. Right? This is our first step. Our second step, there what we will do, we will again redraw this, because these two capacitors, they are again in parallel. Okay. Our second step. So again, this is point A, and this is point B. So this is point A, this is capacitor C, and this is C2, this is C dash, and this is C1. And when we find the parallel capacitance of this two, so we will have net capacitance, let's say C triple dash. And since they are parallel, so we are just going to add them. So C7 is 4 microfarads, so C double dash is again 4. So C triple dash, it is going to be 8 microfarad. Okay? And this leads to point B. So as you can see here, so C1, which is 1 microfarad, it is series, is connected in series to the C triple dash. And C2 and C dash, they are connected in series. So now we have to redraw this again. So our third step. So this is C, and here, and this is getting divided in 2 branches. So here, let's say that you are having C, let's say 4 dash. Let's say that you are having another capacitor thing. So I'm not going to use any more symbols there. I'm just going to write the value. Okay, so that will be more simpler and easier for us. So in this branch, this capacitor will be the effective capacitance of this C1 and C triple dash, and here in this branch it will be effective capacitance. This capacitor will be the effective capacitance of this C2 and C dash. Alright. So when we calculate the capacitance of these two capacitors, so that is going to be around 8 into 1 by 8 plus 1, 9. It is going to be something like 8 by 9 microfarad. Okay. So 8 by 9 microfarad is the effective capacitance of this capacitor C1 and C triple dash. And if I find the equivalent capacitance of this two, C2 and C dash, so C2 is 8 and C dash is 4, so 8 into 4 by 8 plus 4, 32, so it's something like 8 by 3, right? 4 is 32, so 8 by 3, 8 by 3. Okay. And again, they are in parallel. So our fourth step, I'm trying to solve this circuit diagram step by step so that things are very clear to you. But the more you practice solving such questions, so you don't need to do it step by step. But directly, you be able to do it. Looking into the connection, which capacitors are connected in series and which capacitors are connected in parallel. Okay, just looking at the diagram, you'll be able to solve it within one single step. Okay. So our fourth step, so that will be nothing but this C, and let's say that they are in parallel, so we are just going to add them. So 8 by 9 plus 8 by 3, so I think it should be something like 32 by 9, right? So this capacitance value is 32 by 9. And when you add this two, you will get the effective capacitance. Now, the effective capacitance value is known to us, it is given to us, which is 1 microfarad. So we are going to use this effective capacitance and we are going to find the value of this C. Okay, so C net that is mentioned to us, which is 1 microfarad. Now, since these two capacitors are connected in series, so C into 32 by 9 by C plus 52 by 9, which is 1 microfarad. Right. And when you calculate this equation, you should be able to find the C value. So, I'm directly doing it. You should be able to do it. Take this C plus 32 by 9, the other side, and then you solve it. So it would be something 32 by 23. And when you divide it, that value is going to be something like 1.39 microfarad. So this is the value of this capacitance value of this capacitor. Okay. So in this question, it is mentioned that a capacitor is filled with two dielectrics of same dimension, but of dielectric constant K1 and K2. So these are the values of K1 and K2. And we have to find the ratio of the capacities in those two possible arrangements. When we say arrangement, that means we have to insert two dielectric in a parallel plate capacitor, but there are two possible ways how we can insert those two dielectrics in this capacitor. So this is our first arrangement, if you see, and this is our second arrangement. So here, if you see, now both these dielectrics are having same area. Okay, area of this metal plates, which is same as the area of the metal plates, but their thickness is d by 2. D by 2. Remember, d is nothing but the separation between these metal plates. This is our first arrangement, how we can insert two dielectrics. This is the second arrangement. Here the areas are different. Cross-sectional area of the dielectrics are different. It is A by 2 and A by 2. Okay. But their thickness is same, which is same as the separation between these metal plates. Okay. So these are the two possible arrangements how you can insert two dielectrics which is having same dimension between two metal plates. So if we see our first figure, for this arrangement, this capacitor acts as a series combination of two different capacitors. This is how we are going to solve this, okay? Since this dielectrics are inserted in such manner, having same area but their thickness is half the separation between these metal plates. So this capacitor will act as a series combination of two different capacitors. In this case, he is having a dielectric constant K1 and he is having a dielectric constant K2. Right. And for this case, this capacitor will behave as a parallel combination of two capacitors. Parallel combination of two capacitors, where one of them will have a dielectric constant K1 and the other will have a dielectric constant K2. This is how we are going to solve this. So separately we will be finding out the C1 and C2, and we are going to use the series formula and we are going to find out equivalent capacitance for this capacitor. Okay. Now, since for parallel plate capacitor, we have this formula, E equals to epsilon naught A by D, Now this is the capacitance value when the medium between the plates is vacuum. But when we insert a dielectric constant, so the expression turns out to be something like this. Okay, so this is the capacitance value in vacuum, and this is the capacitance value when a medium is inserted. Right. Now for C1, so here it is having a dielectric constant K, and this value is given to us, which is 2. So 2 epsilon naught, and since area is same, which is seen as the area of the metal plates, so that area will be A, but the separation between the plates, we will take it as d by 2. Here, the separation between the plates, we will consider it as d by 2, because this dielectric slab of dielectric constant K1 is having a thickness d by 2, and this entire dielectric is inserted in this capacitor. So that is why we will assume it as d by 2. So that is why we write d by 2 there, and we will have a capacitance value of 4 epsilon naught A by B. So this is the capacitance of this first capacitor with dielectric constant 2. And similarly, we are going to find capacitance of this second capacitor with the dielectric constant 3. So it is going to be 3 epsilon naught. Remember, area of this, again I am mentioning, area of this dielectric slab is same as the area of this metal plate. So that's why E. But this dielectric slab is completely filled between these two metal plates, and which is having this separation d by 2, because we have already mentioned it, right? This dielectric slab is going to cover a distance of, or taken a thickness of d by 2. So that's why it is going to be d by 2 there. So here we'll be having this d by 2 factor there. So if you do the calculation, it is going to be something like this: 6 epsilon naught A by B. So this is how we are going to simplify this. Now since these two capacitors are connected in series, so we are going to use this series formula, which is nothing but 1 by C1 plus 1 by C2. So 1 by C1 is going to be something d by 4 epsilon naught A. Here it is going to be like d by 6 epsilon naught A. If you do the calculation, so 1 by C is going to be something like 5d by 12 epsilon naught A. And this is going to be giving us a net capacitance of 12 epsilon naught E by B.
Okay, so here the capacitance should be 12 epsilon naught A by 5D. So I had not written that 5 there, so please write it down. 12 epsilon naught A by 5D.
So for such arrangement, let's say it is C1, or instead of C1, let's say that it is C dash. That will be more better. C dash is 12 epsilon naught A by T. Right? So this is the capacitance of this capacitor when two dielectrics are arranged or inserted in such a manner. Alright. Now when we go back to this second diagram, here dielectrics are inserted in such a manner that each dielectric, the cross-sectional area of each dielectric is half the area of the metal plate, but the thickness of each dielectric will be same as this separation between the metal plates. So for this we have simplified that this capacitor is nothing but a parallel combination of two different capacitors. How we are going to do that? We are going to separately find capacitance C1 and capacitance C2 of these two capacitors. So C1, now since he is inserted with this dielectric constant 2, that is K1. So it is going to be 2 epsilon naught. Now remember, this dielectric is having an area of A by 2. So this metal plate, which you see, this metal plates will have an area of A by 2. But since this dielectric is assuming this thickness D, so the separation between these two metal plates will be D only. Now that is not changed. Only this area of this metal plate that has changed by A by 2. So instead of A, we will put this A by 2. Remember, A is nothing but the area of the metal plates. But since we have divided this metal plates into two parts, right? So that is why it is nothing but a parallel combination of two different capacitors. The upper one is C1, capacitor C1, and the lower one is capacitor C2. This is how we are going to solve it. So that is why this first part is having an area A by 2 with this thickness or separation D. So let's say 2D. So C1 is nothing but epsilon naught A by D. So this is C1, capacitance of this first capacitor. For this second capacitor, dielectric constant is 3 epsilon naught. Again, area is A by 2 and separation is D. So it is nothing but E by 2 epsilon naught A by D. So our net capacitance, let's just say that it is C dash. So it is nothing but C1 plus C2, because this is parallel combination. So when we calculate, we get something 3, sorry, so it will be something 5 epsilon naught A by 2D. This is the effective capacitance of this arrangement, right? So C double dash is nothing but 5 epsilon naught A by 2D. Alright, so this is how we are going to find the capacitance of these two arrangements. Now what we will do, we will find the ratio of these two capacitances. So that is what we have asked. Here if you see this, ratio of capacitance, that is what it is asked. So C dash by C double dash. So 12 epsilon naught A by D. And that we are doing it. So this 2D by 5 epsilon naught A. Let me do the cancellation. So it's something 24 24. Okay, so here we were having 5 there, 5D, sorry. 5D, okay. So it is nothing but 24 by 25. So this is the ratio. Okay. But here you need to put more effort to understand this part, that how we have inserted the dielectrics, and why this dielectric, after inserting this dielectric, why we have taken series combination, series arrangement for this capacitor and parallel arrangement for this capacitor. Alright, because we are going to have numericals related, as such, many more numericals we are going to see. Okay. So that is what you have to put your effort more to understand why it is series and why it is parallel. So in this question, I said that the figure shows the variation of voltage V across the plates of the capacitors A and B versus the increase of charge Q stored on them. Which of the two capacitors will have highest capacitance? The reason for your answer. So this is V versus Q graph. Okay. Potential difference between the plates and the charge stored in the capacitor. Right. So this is the variation between them. And we are having two capacitors. A and B, and the variation of V with charge for these two capacitors that has been shown to us. Now remember, for such graph, slope, which is tan theta, which is nothing but for this graph, it is V by Q. For this graph, your slope will be nothing but V by Q. And we have this relation which is Q equals to CV. So this capacitance is nothing but Q by V. But since the slope is V by Q, so we are having an inverse relation with this capacitance. So that means the slope is a reciprocal of this capacitance. So if you see slope of A, capacitor A, is smaller than slope of capacitor B. Okay, slope of capacitor A is smaller than slope of capacitor B. Now since this slope is inversely related to this capacitance, to such graph, so therefore capacitance of A will be greater than capacitance of B. Right? So this is how you can answer for such graphs whose capacitance will be more and whose capacitance will be less. Right? All you have to see the slope part. Right? For such graph, V versus Q, your slope is nothing but 1 by C. So that will help you to answer this, answer the comparison, or if you want to compare many more capacitors, so that will help you. Alright? Okay, now if you see this graph, this is my Q versus V graph for parallel plate capacitor. So here if you find your slope there, so that is nothing but tan theta. So for this graph, Q versus V graph, the slope is nothing but Q by V, and which is again equals to C. So for Q versus V graph, your slope is directly proportional, to the capacitance of a parallel plate capacitor. Okay, parallel plate capacitor. Now, if we see this question, now we just say that a figure shows the variation of charge Q versus potential difference of two capacitors C1 and C2. The two capacitors have same plate separation. Right? U1 and C2, we are having two capacitors, and both the capacitors are having same separation, but the plate area is different. The plate area of C2 is double that of C1. Now remember, for a parallel plate capacitor, the capacitance expression is epsilon naught A by D. So it is clearly seen that capacitance of a parallel plate capacitor is directly proportional to the area of the metal plates. So since C2 is having double the area compared to C1, that is why C2 will be twice of C1. Okay. Now since C2 is twice of C1, so if you see this graph, so slope of curve A is greater than slope of curve B. Okay. Now since slope of curve A is greater, and here we can clearly see that C2 is much greater as compared to C1. So this curve A will represent variation for capacitor C2, and curve B will represent variation for capacitor C1. Okay. This is what it is asked, which of the line in the figure corresponds to C1 and C2 and why. So since C2 is having greater value, because this area is double that of C1. So that is why curve A, who is having greater slope, you can see this relation here. So the greater the slope, greater will be your capacitance value. So if curve A is having greater slope, so that is why C2 will represent curve A and C1 will represent curve B, because its slope is quite smaller as compared to A. Okay.